Let's take a look at this interview question, which was asked for a quant researcher role in one of the top companies in quantitative finance. The question says, you play rock, paper, scissors with an opponent, but your opponent cannot play rock. Every time you win $1, and every time you lose $1. When you draw, you get $0. So what should you play to maximize your expected profit? So we are given a scenario, rock, paper, scissors, and it says that we can play rock, we can play paper, we can play scissors. The opponent cannot play rock, so the opponent can play only paper or scissors. And every time we win, we get $1. So plus one. And every time we lose $1. And the question is, what should be our strategy to maximize the expected profit? So let's see how we solve this. Let's first create a payoff matrix to see what all of the possible values are in different scenarios. So in the first column, we have our move, which is either rock, paper, or scissor. And in the next two columns, we have our opponent's move. And as the question says, the opponent can play either paper or scissors. The opponent cannot play rock. So the first column is for paper, and then the second for scissors. Now, when we play rock and the opponent plays paper, we lose. So there's -1 here, indicating we lost $1. When we play rock and the opponent plays scissors, we win $1. So there's +1 here. Similarly, when we play paper and the opponent also plays paper, it's a draw, so it's $0. Then when we play paper, opponent plays scissors, we lose $1. When we play scissors, opponent plays paper, we win $1. And when we play scissors, opponent plays scissors, it's a draw once again, so $0. So this is our matrix showing all of the different scenarios on how they play out. Now, just based on this payoff matrix, we cannot really estimate the expected values because we don't really know what's the likelihood of the opponent playing paper or scissors. So what we can do is we assume that the probability that the opponent plays paper is, let's say, P. And so the probability that the opponent plays scissors becomes 1 minus P. Now, we know the probability for these two scenarios and we know the payoff amount. So we can calculate the expected values for each of these different scenarios by taking the product of probability and the amount that we win or lose. So let's see how we can do that. For the case of rock, this would become -1 times P. So minus P plus 1 times 1 minus P. 1 minus P. So this becomes 1 minus 2P. When we play paper, in that case, it becomes 0 times P, 0 times P, which becomes 0, and -1 times 1 minus P. So this becomes P minus 1. When we play scissor, opponent has paper, so this becomes +1 times P. So P plus 0 times 1 minus P, which is 0. So this becomes P. So we have 1 minus 2P, P minus 1, and P for the expected payoff for each of the different scenarios. Now, what we need to do is we need to estimate uh, how does this payoff vary based on different values of P. So as we just saw, we already calculated this, the expected payoff for each move. When we play rock, the expected payoff was 1 minus 2P. When we played paper, the expected payoff was P minus 1. When we play scissors, the expected payoff was P. Now, the expected payoff, we need is what we need to maximize. So for different values of P, the expected payoff would be different for when we play rock, when we play paper, when we play scissors. It could be for some values of P, the expected payoff is the highest for the case of playing rock. For some other value, it's highest for uh, scissors, and so on. So how do we estimate that? We will check the values of P. So let's say rock, the expected payoff for this scenario when we play rock is the highest. So what does that mean? That means that 1 minus 2p, 1 minus 2p is greater than both of these payoffs, this and this. So it has to be greater than p minus 1, and also 1 minus 2p has to be greater than p. Yeah. So similarly, for a different scenario, the payoff for the case of paper would be the highest. So what we'll do is, actually it cannot be the highest because as you can see, this is p minus 1, and whereas scissor is p. So p minus 1 for positive p, a non-zero positive p would be obviously less than p. So either the rock would be the highest or the scissors would be the highest. In case of rock, as we saw, we'll solve these inequations to see where does p lie. And for the case of scissors, we can write similar equations wherein we write the expected payoff, which is p is greater than 1 minus 2p, and p is greater than p minus 1. Okay, so this is obviously always true. This doesn't give us any information, or does it? Yeah, no, it doesn't. And p is greater than 1 minus 2p. We can solve this to see where does the value of p lie. So let's see in the next slide. So we want to maximize your expected profit. So we need to compare these expressions as we just saw. The expected payoff in the case of playing rock was 1 minus 2p. For the case of paper was p minus 1. And for case of scissor was p. For which p is rock best? So 1 minus 2p should be greater than the expected payoff for scissors. So it's greater than p. This gives us 1 greater than 3p, which means p is less than 1/3. Also, because we are saying that rock payoff is the best, it means the payoff for rock should also be greater than the payoff for paper, which means 1 minus 2p should also be greater than p minus 1. So you get p is less than 1/3. So so from both of these two ranges, this one satisfies both of these criteria. So for p less than 1/3, rock is the best. For which p is scissors the best? We say scissor greater than the payoff for playing scissor greater than the payoff for playing rock. This gives us p greater than 1 minus 2p, and this gives us p greater than 1/3. Similarly, we write the equation for scissor greater than paper. So p greater than 1, sorry, p greater than p minus 1, which is always true. So p greater than 1/3, scissor is the best. For p equal to 1/3, rock and scissor have the same expected payoff. So now what should you actually play? So if we know the opponent's distribution, that is, we know the value of p, we can play the best pure strategy as above, which we just saw in the previous slide. If the opponent chooses randomly between paper and scissor, that is p is 1/2, 50%, the payoff becomes for playing rock becomes 0, for playing paper becomes negative 1/2, and for playing scissors is 1/2. So always play scissors when we don't know what the opponent is going to play. If you have no information about P, assume opponent plays paper and scissors at random. Always play scissors. So there are two cases. Either we have no P, what the opponent's strategy is, that would give us P, and we can choose our strategy accordingly. If we don't know P, we assume P is 1/2. Opponent's choosing randomly, and we'll always pick scissors. So this is a general insight. Although the question is pretty much complete, we solved the problem. We came up with the optimal strategy based on the different scenarios and what the value of P would be. Either we know or we don't know. We saw the strategy for both of the cases. If your opponent cannot play rock, always play scissors to maximize your expected profit. assuming their choice between paper and scissors is not biased against you. Scissor beats paper and draws against scissor. Paper by contrast, and of course you know how the game works. And yeah, so this is pretty much it. This was a simple, straightforward interview question which was asked for a quant role. And it's good to practice this beforehand. Otherwise, this could leave you struggling on the spot if you haven't practiced beforehand. So I hope you found this video helpful. Thanks for watching. Do let me know in the comments if you have any particular preference on the kind of questions that you like to see. Also, you can visit datalooper.com for a lot of different articles and questions asked for different roles in quantitative finance, data science, machine learning, and AI. Do let me know in the comments if you have any feedback or if you'd like to see anything in particular. Thanks for watching, and I'll see you in the next video.